For Chapter 4, Part B, we're going to be exploring chemical equations, which includes balancing chemical reactions and also looking at reaction types.
Those should help as well. All right, let's move on to chemical reactions. So what is a chemical reaction? A chemical reaction occurs when chemical bonds between atoms are broken or formed. All right, so basically you are breaking bonds and forming new ones. You're making new compounds. You are rearranging atoms, essentially. So chemical reactions contain two general components. First, the reactants. And what the reactants are is they're the components that are mixed together. It's what you put in the flask. So if you're going to do a chemical reaction, it's what you're tossing in. What the products are then is what you're getting out of the flask when you're done. What was made? What's the end, the final product? When we represent chemical reactions on paper, we have the reactants always on the left-hand side, and then an arrow pointing to the products on the right-hand side. So here's an example of a chemical equation, how we represent a chemical reaction. So in this chemical equation, we have 4 aluminums reacting with 3 oxygen molecules to form aluminum oxide. Okay, so the reactants in this case are aluminum and oxygen because they are on the left side of the equation, and the arrow is pointing to the product, which is aluminum oxide in this case. So you can sort of think of that arrow as an equal sign. I'm adding these two and it's equaling the product. Okay. Some other key points of a chemical equation is you'll notice that there are these coefficients in front of each element or compound. So those coefficients are going to be very important when we talk about balancing equations. Those coefficients are making sure the atom count is the same on both sides. And we'll get into that a little bit more in a moment here. One other thing I did want to point out, however, is that notice there's also little letters after each element or compound. Okay, so what these letters are for is they're telling us what form, what physical phase that particular element or compound is in. So for aluminum, it has an S after it. What that's saying is it's solid. They took a solid piece of aluminum and put it in the flask. Oxygen has a G. That is just saying that it was a gas. So they pumped oxygen gas into the flask. When the reaction was complete, the product, aluminum oxide, has an S by it, so it was a solid. Other phases you might see are liquids. That will have an L by it. Water is often going to be in the form of a liquid. You'll also see aqueous, which will be an AQ. That is simply a solid that was dissolved in water. Okay, so it's not a liquid because it's not pure because it's 2 components mixed together. That would be aqueous. So let's look a little bit more at these coefficients that I mentioned previously. They are now in red. So those coefficients are helping us to make sure that there are the same atom counts on both sides of the equation. So why do we need the same atom count on both sides of the equation? We need it because of the law of conservation of matter. And what the law of conservation of matter says is that the atom count must be the same on both sides. Energy cannot be created or destroyed. Well, neither can atoms. Okay, so if whatever I put in the flask, I need that same amount of stuff coming out of the flask. So that's what the atom count is saying here. So how do you figure out the atom count? Well, you take the coefficient and you multiply it by the subscript. So I have it color-coded here so we can see it a little bit better. So notice coefficients are in red. The subscripts are in yellow. Okay, so on the reactant side, I am going to calculate how many aluminums I have, how many oxygens I have. However many aluminums I have on the reactant side, I need to have the same amount on the product side. Same with the oxygens. So let's count. For aluminum, I have 4 of them. For oxygen, I'm going to take that coefficient of 3 and I'm going to multiply it by that subscript of 2. So 3 times 2 tells me I have 6 total oxygens on the reactant side. Now I'm going to go to the product side. I have a coefficient of 2. So I'm going to take that and I'm going to multiply it by the subscript of 2 to give me a total of 4 aluminums. So that checks out. 4 aluminums on the reactant side, 4 on the product side. Good there. Now I'm going to do it again for the oxygen. So this coefficient of 2, it applies to every element in that compound. So it's going to apply to aluminum. It's also going to apply to the oxygen. So I'm taking 2 times 3 in this case to get a total of 6 oxygens. So atom count is the same on both sides, 4 aluminums and 6 oxygens. When we balance our own equations, what we're going to be doing is we're going to be changing the coefficients. Those numbers in red, those are the numbers we control, those are the numbers we can change. We cannot change the subscripts, the numbers in yellow. Those have to stay the same. If we change the subscripts, we are changing the chemical compound. So only the coefficients can be used or changed to balance the reaction. Subscripts cannot be changed.
Let's look at another balanced equation. So remember, to balance an equation, we need the same number of each atom on the left side of the arrow and the right. This is achieved by changing the coefficients, not the formulas themselves, so no subscripts can be changed. So looking at this example here, to figure out the atom count on both sides, to calculate the number of atoms, we take the coefficients, the number in front of the element or compound, and multiply it by the subscript of each element or compound. So looking at the reactant side of the equation, we can see that iron is going to have 4 atoms on the reactant side. We figured this out by taking the coefficient in front of that iron 3 oxide compound and multiplying it by the subscript after iron. 2 times 2 gives us 4 iron atoms. For oxygen, we're still using the coefficient of 2 because that number 2 applies not only to the iron in that iron 3 oxide compound, but also to the oxygen. So to figure out the number of oxygens, we're taking the coefficient of 2 and multiplying by the subscript on oxygen, which is 3. 2 times 3 gives us 6 oxygen atoms on the reactant side. For the carbon, the coefficient is 3 and the subscript, well, there isn't one. So when there is no subscript, we use a subscript of just 1, giving us a total of 3 carbon atoms on the reactant side. Now looking over on the product side, coefficient of 4 in front of the iron, there's a subscript of 1 after. Since there is no subscript, we assume it's a 1. So 4 times 1 gives us a total of 4 iron atoms. Notice it's balanced on both sides for the iron. We have 4 on the product side and 4 on the reactant side. Putting a 3 in front of the carbon dioxide gives us a total of 3 carbons. You can see that at the bottom here. For the oxygens, we take that coefficient of 3 and multiply it by the subscript on oxygen, which is 2. 3 times 2 giving us 6 oxygen atoms. The atom count is the same on both sides, making this a balanced equation. During the lecture portion of the videos, we will be working through and figuring out how to come up with those coefficients when they're not already present.
All right, so some other equation details before we look at some next topic is we discussed this previously, the small letters present after each element or compound indicates the phase. So we have solid, gas, liquid, and then aqueous. So in the example down here, sodium chloride being table salt, that's a solid, right? I said water is a liquid at room temperature. So if we take a solid table salt and we put it in water, what happens? It dissolves. Okay, and when it dissolves, we have now made an aqueous solution because it is a mixture of solid sodium chloride that has been dissolved in water. All right, so let's look at some different types of synthesis or combination reactions. We have 5 different types of reactions that we're going to be learning, and you need to be able to recognize these reactions and label them correctly. Okay, so the first type we're looking at is synthesis. It is also called a combination reaction. It is called this because you take two things, two reactants, you're adding them together to make one product. Okay, so the example that I have here is taking H2 gas, O2 gas, combining them in a combination reaction to synthesize water. So the next type we're going to look at is a decomposition reaction. And this is kind of the opposite of a combination reaction, because in this case, on the reactant side, we have one compound, and that compound is breaking apart. It's decomposing into two separate products. Okay, so with synthesis, we had two things on the reactant side combining to form one thing. But with decomp, we have one reactant compound breaking apart into two products. Right, so the example shown here is nickel 3 oxide breaking apart to form nickel and oxygen, so into its elemental form. The other examples that I have down here are some different acids that are decomposing in decomposition reactions. Notice in all of them we have one reactant, and that reactant is breaking apart and decomposing into two products. Okay, so that's how you can identify these as decomp, because I have just one reactant breaking apart into two products. In this case, these acids are all decomposing into water and their counterparts. The next type of reaction is a single displacement reaction. With a single displacement reaction, we have an element or ion basically switching spots with a compound. So how do you recognize this as a single displacement? Well, you have a metal by itself in its elemental form, and it is going to switch places with another metal that's in a compound. Okay, so in this example down here, we have zinc by itself in its elemental form, and it's going to kick copper out of its spot so that zinc is now with SO4 in a compound and copper ends up by itself. So it's replacing or displacing one element for another. Now, in the case of single displacement, remember that zinc is going to take the place of copper. Zinc will never take the place of SO4. Because we always want a cation with an anion. We always want a positive with a negative. We want the metal with the polyatomic. What I mean by that is you're not going to see zinc and copper forming a bond together, because they're both metals, they're both cations, both of them have positive charges, and positives, likes do not attract, likes repel. Okay, we need opposites attracting here. You're going to have to be able to predict products of some of these reactions, so that's why I'm pointing that out here. So let's look at the next example. So we have aluminum by itself. So think of that as being the A in this diagram up here. And what that A, that aluminum, is going to do is it's going to go over and it's going to kick out B. So in this case, B would be copper or sulfate. What is it going to take the place of? It's going to take the place of copper. Because aluminum's a metal, so it's going to take the place of another metal. So now, on the product side, we have aluminum with the sulfate and copper by itself. Okay. Now, what is the driving force of these reactions? Well, we said a metal always replaces another metal. So these A and B that we have up here, okay, these are usually metals. Not always, but usually. C generally represents the nonmetal or the polyatomic. What drives these reactions is the more active metal replaces the less active one. And we're not going to get too much into reactivities of metals, but I do want you to be able to know the reason behind it. Okay, you don't have to memorize the table of the reactivities. Double displacement reaction. So what do we have here? In this case, it's very similar to single displacement because we're switching places. But in this type of reaction, instead of having an element or a metal alone by itself, we have two compounds reacting with each other. Okay, so there's no one by themselves. So we have two compounds on the reactant side, and we have two compounds on the product side. So that's how you can identify it as double replacement. Two compounds switching partners forming two new compounds. So in this case, we have calcium bromide and silver 1 nitrate. So calcium bromide, the calcium is going to switch partners with the silver because the metals switch with the metals. You're not going to see the two metals together, so they're going to switch partners. So calcium is going to steal silver's partner, the NO3, so that on the product side, we have calcium nitrate. The silver now isn't going to be with nitrate anymore on the product side. Instead, silver is going to be with bromine. So we have silver 1 bromide as a product. Now, the driving force for these reactions is the formation of a solid. So if you'll notice these little symbols down here, right, they tell us the physical state. We have aqueous for the calcium bromide, aqueous for the silver nitrate, and then over on the product side, notice we have one aqueous, calcium nitrate, but the other one's a solid, because the formation of a solid is what helps drive these reactions forward. Well, how do we figure out if a solid forms or not? Well, these reactions, since they form a solid, they're often referred to as precipitation reactions. Okay, so what is a precipitation reaction? It's when you combine two liquids and you get out a solid. So what a precipitate is just another word for a solid. So if I say, okay, I mixed these things together and out came a precipitate, what I'm saying is out came a solid. I saw a solid form. All right, so we're going to use solubility tables to predict if a product will form. Because when you do these reactions, you're not going to be given this S here and this aqueous here. You're going to have to figure those out using solubility tables. So these are the tables that we are going to be using to predict if a compound will form a solid and if a compound will not form a solid. So you'll notice we see the words soluble and insoluble. Okay, so what soluble means is the substance is dissolved. So no solid formed. So if you hear the word soluble, that means it dissolved. The word insoluble then will mean that a solid or a precipitate has formed. All right, so how are we going to be applying these tables? What this table is saying, this top one, is that looking for these ions that are in the compounds, if any of these ions are present, they can be soluble, so they can dissolve. If they're with an exception over here, that means they will be insoluble. Let's apply and use it. We'll take a little closer look at this. Okay, so here is a picture of a reaction where we are mixing potassium iodide with lead 2 nitrate. And you'll notice you see this yellow foggy material forming. What that is it's a bright yellow precipitate. It's actually a solid. So we know that when we mix potassium iodide with lead 2 nitrate, that a solid is going to form. Our job is to figure out what solid. So I have the reaction equation written down here. Reactants on the left-hand side, arrow pointing to the products. When I mix potassium iodide with lead 2 nitrate, I'm switching partners because it's a double replacement reaction. So potassium is going to take the place of lead. Lead is going to take the place of potassium. They're switching partners. So on the product side, I have lead 2 iodide and potassium nitrate. Now I'm going to use those solubility tables to figure out, is it lead that made that solid yellow precipitate, or is it potassium nitrate? So what we have on this slide is a little closer look on the molecular level of what's happening. So if you notice, I have the reactants over here on this side, and then I have my arrow pointing to products. So what happens when we take ionic compounds and we put them in water is they dissociate into their ions. We talked about this property with ionic compounds, how they break apart into the cations and the anions, and that's why they can have some conductivity. Okay, that's why they can conduct or have the possibility to conduct electrical currents, because they have these ions, these charged ions floating around in the water. So with potassium iodide, we have little potassium, little K+ ions, and we have little iodine, I- ions floating around. Now, what's nice about this is we have two aqueous solutions, aqueous just meaning that our solids were dissolved in water. And since those ions are now separated into their counterparts, it makes the reaction happen really quickly because we have all these ions just floating around. So when they bump into each other, they connect and form a new compound, essentially. So on the product side, we can see all the ions floating around there. So what we need to figure out is which ions are getting together and forming this yellow precipitate. Okay, so let's look at that solubility tables to figure that out. So what I want to do here is, here are our two possibilities that we were looking at on the previous reaction equation. We had lead 2 iodide as one of the products, and we had potassium nitrate as one of the products. So we're going to take these ions, find them on the table, and figure out if they are soluble, meaning dissolved, or if they are insoluble, meaning yes, precipitate formed. All right, so I'm going to start with my potassium nitrate. So to do this, I can either look for the potassium ion, K+, or I can look for the nitrate. It doesn't matter which one. Either one will give me the same results. So say I look for my potassium first. So what I do is I go over to the table and I find where K+ is. And what it tells me, the table says that K+ is going to be soluble. Now that means it can be soluble. It doesn't mean it's always going to be, because I need to follow this line over to where the exceptions are. But notice the exceptions in this column, there's none. So what that means is that potassium, K+, is going to be soluble all the time with no exceptions. So that means it's always going to dissolve in water. It's never going to form a solid. So that tells me that KNO3 is definitely not going to form a solid, because it's going to be soluble no matter what. Now, if I had decided to find NO3 first instead, the anion portion of that same compound, right? Notice it's telling me that it can be soluble, and I'm going to follow over to the exceptions, and once again, no exceptions. So that means if I have a nitrate anion, it is going to be soluble in water all the time, no exceptions. Okay, so it's giving me the same answer, notice, no matter which ion I looked up on the table. So KNO3 is soluble. It's not going to be the solid. That means lead 2 iodide is probably going to be the solid, but let's look and make sure. So when I'm looking at this table, I can look up either the lead, Pb, 2+, or I can look up the iodine minus. Now when I look at this table, the iodine minus I can find a lot easier. So when I find that anion, it's telling me that it can be soluble. But now when I follow it over to the exceptions, it's saying iodine soluble unless it's with one of these 3 metals. Notice one of those 3 metals is lead 2. So that's saying that iodine, yes, it can be soluble unless it's with silver, lead, or mercury, and it is with lead. So the exceptions are telling us that a solid will form if it's with one of these guys. Iodine is with one of those guys, so lead 2 iodine is a solid. So we have solid for the lead 2 iodide, and then we'd put an AQ by the potassium nitrate because it's soluble all the time, no exceptions. Some other common reactions that we need to know are listed on this slide here. The one that I want you to focus on most is this combustion reaction at the top here. So what a combustion reaction is when we have a hydrocarbon, so a hydrocarbon being a compound with just carbon and hydrogen present, reacting with oxygen to form carbon dioxide and water. So what's special about this type of reaction is you're always going to have a hydrocarbon mixing with oxygen. Those are always going to be your reactants. So oxygen will always be one of your reactants. And your products are always going to be carbon dioxide and water. So if you see two products, carbon dioxide and water, you know it's a combustion reaction. So the reason I'm keep repeating this section is because you're going to need to be able to identify if a reaction is a combustion reaction. And the telltale signs of that are the products are carbon dioxide and water every time. Okay. The other reaction I have on this slide down below is iron and oxygen combining to form iron 3 oxide, which is rust. Okay. That one you won't have to memorize the reaction layout or be able to identify. So let's look down below at this last type of reaction. And this is an acids and bases reaction where we're seeing a proton transfer. Now I'm just introducing this reaction here now because we're going to look at this a lot closer in later chapters. But while we're talking about reaction equations, I just wanted you to see a quick example of that. So what we have happening here is we have an acid, in this case hydrochloric acid, HCl, a base, NaOH, sodium hydroxide, and when they react together, a neutralization of sorts happens because our products are going to be water and salt, right? So we'll explore this reaction in further depth in a later chapter. I just wanted to introduce the layout of it now. So out of these reactions, the one I really want you to remember is this combustion reaction here, okay? Remember that it is always a hydrocarbon reacting with oxygen and its products are always carbon dioxide and water.
Another common type of reactions that we'll see are reduction-oxidation reactions, also known as redox reactions. These occur when there's a transfer of electrons from one reactant to another. We're going to explore these types of reactions in more detail in Chapter 8. But we want to introduce them now because most of the time, a lot of the single replacement reactions that we have looked at are also redox reactions. So what I have shown here are the half reactions. So we have copper with a 2+ charge on the reactant side. We have magnesium by itself, so it has no charge, meaning since there's no charge in the upper right-hand corner, its oxidation state or charge is 0. On the product side now, we have magnesium with a +2 charge, and now copper's by itself. Well, when copper's by itself, it's neutral or has a charge of 0. So what we're seeing here is that copper on the reactant side is going from a +2 to a charge of 0. So in order for it to go from a +2 to a 0, it's gaining 2 negatively charged electrons. So you can see in the half reaction here, we have the copper 2+ gaining 2 negatively charged electrons to get that copper neutral. So it gained 2 electrons from the magnesium. So this transfer of electrons makes it a redox reaction. This reaction in particular, the copper, since it's gaining electrons, the copper is reduced. And the magnesium, we'll see in a second here, is actually losing electrons, so the magnesium is oxidized. So when we have redox reactions, they always happen in pairs. One element or compound is reduced and another is oxidized, meaning one has to gain electrons because it's gaining it from one that's losing. So let's look at what's happening to magnesium. We can see for magnesium here that it's going from a 0 to a 2. So why is it going from 0 to plus 2? It's losing 2 negatively charged electrons. It loses those 2 negative electrons to get that plus 2 charge. Just pointed out on the previous slide that a lot of redox reactions are also single displacement reactions. So I wanted to show some more examples of that. So here we have 2 examples of single displacement reactions where we have one element by itself reacting with a compound, switching partners so that the element that was by itself on the product side is now in a compound, and it kicked out one of the elements that was in a compound so that it's now by itself. So let's look what's happening with these two. So if we isolate, we see that zinc, since it's by itself on the reactant side, is neutral, has a charge of 0. Copper, since it's with a compound, more specifically an ionic compound, it has a charge of plus 2. On the product side, zinc is now in a compound, so it has a charge. Copper is by itself, so it's now went from a plus 2 to 0. So there's a transfer of electrons here. We have zinc giving up 2 electrons to go from a 0 to a plus 2 state, and it's giving those 2 electrons to copper so that it can go from a plus 2 to a neutral state. You can see a similar occurrence with the aluminum and copper in the second example.